밤이 흐르고 흐르면 누군가가 나를 떠나버려야 한다는 그 사실을 그 이유를 이제는 나도 알 수가 있어요. 사랑을 한다는 말을 못해서 어쨌거나 지금은 너무.
In this lecture, we'll focus more on the proof of the classification of modules over a PID. In particular, in the last lecture, we showed how to prove the existence statement for the classification of modules over a PID in invariant factor form, assuming the proof of this theorem 4. We started to prove theorem 4, but we didn't finish it. So I'm going to start by saying that this theorem, the argument that's given in Dummit and Foote, is significantly longer and more complicated than anything that we have proven so far in Math 206. And I'm going to present the full proof of this result for you, partly just to show you that things do get more complicated, that eventually, if you go on in this kind of algebra, you will encounter arguments that are more complicated than the types of things we have seen before. You don't need to know how to prove this theorem for the final exam for Math 206B, and you won't really need to know it for the next quarter either. All right, so let me start by recalling what this theorem says, and then where we are in the proof so far. So what's the setup? R is a PID, M is a free R module of rank n, and n is a submodule of M. Then n is a free module of rank m, where m is less than or equal to n. And there exists a basis, y1 up through yn of m, so that a1, y1, a2, y2 up to am, ym is a basis for n, where what are these ai's? a1 up through am are non-zero elements of R, satisfying the divisibility conditions. A1 divides A2, A2 divides A3, up to AM minus 1 divides AM. And where were we so far in this argument? So when n is the trivial zero module, there's nothing to prove. So let's suppose that it's not. And the first clever idea was to consider any R module homomorphism from M to R and look at the image of n under that homomorphism. That's a submodule of R, so it's a principal ideal because R is a PID. So phi of n is generated by a phi for some, is the ideal generated by a phi for some element a phi of R. So for each phi, we get some element a phi. And we let sigma be the collection of principal ideals that arise in this way. So the ideals generated by each of these a phis. Sigma is non-empty because the zero ideal is in there. And by theorem 1 that we proved at the beginning of the last lecture, this one that gives several equivalent ways of saying that an R module is Noetherian, sigma has a maximal element under inclusion. So let's name that. That's some principal ideal, A nu. And what does that come from? It corresponds to some R module homomorphism nu from M to R. All right, so if nu of n is generated by this ideal, or is this ideal generated by a nu, then in particular, a nu, this ring element, is in the image of nu restricted to n. So we name that element. There's some y in n, so that nu of y equals a nu. And for ease of notation, we're going to write a1 instead of a nu. So labeling this with the number 1 sort of hints that a major idea in this whole proof is going to be induction. All right, so the first thing we have to do is show that a1 is non-zero. So what do we know about this ideal generated by a nu, or a1 now, is that it's a maximal element of sigma under inclusion. Every principal ideal contains the zero ideal. So the zero ideal is not going to be a maximal element under inclusion unless it's the only element of sigma. So we just need to show that sigma has some ideal in it that is not the zero ideal. And yeah, so that's all we need to do. And we'll do that by actually writing down a homomorphism so that the corresponding ideal generated by a phi is not zero. We just need to find some R module homomorphism so that the image phi of n is not zero. All right, so what we're going to do is choose any basis for m, x1 up through xn. So m is a free R module of rank n. That means that it's isomorphic to a direct sum Rx1 plus Rx2 plus Rxn, where I'm saying plus, but I mean direct sum. And we can define the projection onto the ith factor of this direct sum decomposition. So pi I going from m to r, where you just take an element of m, which you can think of as an element of Rx1 plus Rxn, and you take, so each one of these, it's like some ring element times x1, some ring element times x2. So you just take the ring element in the ith coordinate. So this is the natural projection onto the ith components. And n is not 0. That means that at least one of these pi I of n's is not 0. That if you take the projection onto the ith coordinate and see that it's always 0, that would mean that every element in n was 0. Okay, so one of these pi I of n's is not 0. So in particular, each one of these pi I of n's gives an element of sigma. So there's some non-zero element of sigma. So A1 is not 0. All right, so I'll pause and erase, and then we'll talk about what to do with this element A1. The next big piece of this argument is to show that A1 divides phi of y for every R module homomorphism phi from M to R, where, remember, where does this y come from? Y is this element in N that we know you apply this R module homomorphism nu, and you get A1, which is this generator for nu of N. All right, so R is a PID. So the first clever idea here is that we're going to consider the ideal generated by A1 and phi of y. And because R is a PID, we know that that ideal is principal. So we'll name a generator for it. We'll suppose that it's generated by D. So D is a divisor of A1 and a divisor of phi of y in R, because what is the generator for the ideal generated by two elements in a PID? It's a GCD of those two elements. So D is a divisor of A1 and D is a divisor of phi of y in R. So what does that mean? That means that there is an R linear combination of these two elements giving this GCD. So D equals R1 A1 plus R2 phi of y for some ring elements R1 and R2. And now we're going to show that the ideal generated by D is the ideal generated by A1. And since D divides phi of y, if we know these ideals are the same, then that's going to imply that A1 divides phi of y, and we'll be done. So we've now just taken this goal here, and we've changed it into showing that these two ideals are the same. And containment one way is pretty clear. We know that D divides A1, so the ideal generated by A1 is contained in the ideal generated by D. So how do we get containment the other way? Well, this is also a clever idea here. We know that the ideal generated by A1 is a maximal element of sigma. So if we can show that the ideal generated by D is contained in some element of sigma, then we know that the ideal generated by D has to be equal to the ideal generated by A1 because of this maximality, right? If there's another element of sigma containing the ideal generated by D, then that's a problem because A1 is a maximal element under inclusion. So if we can show that the ideal generated by D is contained in any other element of sigma, that other element of sigma must be equal to A1, the ideal generated by A1, which shows equality, that the ideal generated by D is the ideal generated by A1. So I find this idea very clever. So how are we going to do that? How are we going to show that the ideal generated by D is contained in some element of sigma? Well, where do elements of sigma come from? They come from the image of n under R module homomorphisms from M to R. So we're going to cook up the correct R module homomorphism from M to R that's going to force D to be in that image. Okay, so we're going to define psi to be R1 nu plus R2 phi. So this is an R linear combination of R module homomorphisms from M to R, so this also is one. And the claim now is that this image, psi of n, is the ideal generated by D. And if that's true, then this psi of n is going to be an element of sigma, and then we're done. Because we'll see that the ideal generated by D is an element of sigma, and equality holds here by this maximality. Okay, so why did we choose this particular homomorphism? Because we know that when we evaluate this homomorphism at y, we're going to get D. So let's check that that's true. What is psi of y? It is R1 nu plus R2 phi of y, which, this is an R module homomorphism. This is R1 of nu of y plus R2 of phi of y. And what is that? That is D, because nu of y is A1. So that is exactly D. So now D is in psi of n, and therefore the whole ideal generated by D is in this image psi of n. Psi of n is a principal ideal of R. It's generated by some A psi. So psi of n is an element of sigma. And now we have this contained in an element of sigma. So by maximality, the ideal generated by A1 is this ideal generated by A psi. And this D sandwiched in the middle, this ideal generated by D, is equal to both of these things. Okay, so that was a pretty clever argument with several steps to show that A1 divides phi of y for every R module homomorphism phi from M to R. It's not totally clear right away what we're going to use that for. So I'll pause and erase and show you the next big piece of this argument. We know that this ring element A1 divides phi of y, where remember y is this element of n that maps to A1 under this R module homomorphism nu that we got from finding a maximal element of sigma. This A1 divides phi of y for every R module homomorphism phi from M to R. All right, this is true for all of them. What R module homomorphisms do we want to apply this to? We can apply this to each of the projection homomorphisms pi I that we talked about earlier. So these come from choosing any basis x1 up through xn of M. We get these projection homomorphisms. So what do we get from applying this fact to these projection homomorphisms is that A1 divides pi I of y for each I. What does that mean? We can write pi I of y as A1 times some ring elements. So let's say A1 times bi for some bi in the ring. And now we're going to find a really important element for this argument, which is y1. It'll be given as a sum from I equals 1 to n of bi times xi. So these bi's, these are these ring elements that we get from the fact that A1 divides pi I of this special element y. And these xi's, this is the basis that we started with, the just like random basis that we chose at the beginning of this argument to get it going. Okay, so note what is true about this element y1. A1 times y1 equals y, because if you just look at what happens in each component, we see that the ith component of y expressed as a linear combination of this basis x1 up through xn is given by A1 times bi. So that matches up with what happens here. Okay, so what else do we know? We know that A1 is nu applied to y. And we know that A1 a1y1 is y. So y, just replace that with a1y1. And now because nu is an R module homomorphism, nu of a1y1 is a1 times nu of y1. But what does that mean? We have a1 equals a1 times nu of y1. This is an equation in R, and R is an integral domain. We already know that a1 is not 0, so we can cancel these a1s on both sides. So so the only way for this to happen is for nu of y1 to be equal to 1, the identity of R. Okay, so now we're ready to describe a big idea behind this argument. And I would have wanted to start with this, but I can't make this statement until we've defined this element y1. So it takes a while to get here, but if I were to think about how this argument actually works, the main idea is that you can build this good basis for m and this good basis for n, meaning ones that satisfy the divisibility conditions you need, one element at a time. And what are our first elements of these bases going to be? The first element in the basis of m is y1, and the first element in the basis of n is going to be a1y1, which is y. Okay, so we're going to prove two things. First, that m is a direct sum of ry1 plus the kernel of nu. And n is equal to a direct sum of ra1y1, direct sum n intersect the kernel of nu. So remember, this direct sum means that every element of m can be written uniquely as something in ry1 plus something in the kernel of nu. Okay, so once we have these two results, the rest of the proof is not going to be so bad. It will go by induction. So we'll have our y1, our a1y1, and we'll continue in this way. We'll get a y2 and so on. All right, so let's prove A. And what do we need? We need that every element in M can be written as something in here plus something in here in a unique way. So first, let's just see that everything can be written as something in here plus something in here, that it's a sum of these two submodules. All right, so let's take any element x and m. And we're going to write x in a kind of clever way that works in this argument. X will be nu of x times y1 plus x minus whatever that was. So what's the idea? Clearly, nu of x times y1 is in r times y1. So we want to write x as something in ry1, some ring element times y1, plus something that's in the kernel of nu. So nu of x isn't such a crazy ring element to choose. So this is one way to think about what's going on here. So this is definitely true. So now what we need is we need this remaining thing that we're adding to be in the kernel of nu. And we're going to check that that is true just by applying this R module homomorphism and seeing what we get. Well, nu is an R module homomorphism. So we get nu of x minus nu of x times y1. But it's an R module homomorphism, so you can pull out this nu of x, and we get nu of x times nu of y1, which we know is 1. So this is nu of x minus nu of x times 1, which is 0. So what have we seen? Everything in M can be written as something in ry1 plus something in the kernel of nu. But we still have to show that this is actually not just a sum of these two submodules, but a direct sum. So I'll pause and erase and show you how to see that directness. I just want to point out, even though checking this statement is easy, once you remember how to write x in the correct way, I don't think it's so clear that this is the obvious thing to do when working with this general element x. We have seen that M is a sum of these two submodules, ry1 and the kernel of nu. And we want to see that it's a direct sum. And one of the equivalent ways to see that this was a direct sum was to show that there's no intersection between these two submodules. So let's take an element of ry1 and ask what it means for that to be in the kernel of nu. So let's suppose ry1, where now r is a ring element, is in the kernel of nu. Well, what is nu of ry1? There's an r module homomorphism, so this is r times the kernel of times nu of y1, which is r times 1, which is r. So if this is 0, then ry1 equals 0. So r equals 0. Like only the 0 element in ry1 is also in the kernel of nu. So this is one of those equivalent ways to see that a sum of two submodules is actually a direct sum, that it's isomorphic to the external direct sum of these two R modules. Okay, so that completes the proof of part A. So now let's do part B. And part A is going to be a guide for how to do this. So we have x prime, or okay, so to do part A, we started with an arbitrary element x and m. Here we'll start with an arbitrary element x prime in n. And we want to show that it's a sum of something in R a1 y1 and something in n intersects kernel of phi. All right, so same idea as in A, we have a decomposition. Now it doesn't feel like it comes out of nowhere anymore. We can write x prime equals nu of x prime times y1 plus x prime minus whatever that is, nu of x prime times y1. But now, here, it was clear that nu of x times y1 was in ry1. It's not immediately clear that nu of x prime times y1 is in r a1 y1. So what do we need is we need to know something about nu of x prime. And what we need is that we need that a1 divides nu of x prime. But what is a1? It's a generator of nu of n, of the image of this R module homomorphism nu applied to n, this ideal of R. So we have some element, nu of x prime, that the generator of this whole image has to divide that particular ring element. Like that's what it means for it to be a generator. So a1 divides nu of x prime. So that means that we can write nu of x prime as b times a1 for some element b in the ring. So I need a little more space, so I'll pause and erase and then show you first that x prime can be written as something in R a1 y1 plus something in n intersect kernel of nu. And then I'll show you that not only is n the sum of these two submodules, but it's a direct sum using the same idea that we saw up here. Let's finish the proof of B. Now that we know that nu of x prime is something in the ring times a1, we can go back up to this decomposition here and write x prime equals b a1 y1 plus x prime minus b a1 y1. And okay, now this first term is clearly in R a1 y1. And this second term is in the kernel of nu. Why? Well, just apply nu to it and do the same kind of thing that we did in part A. But it's also in n because, sorry, these should be x primes. It's also in n because x prime is in n and a1 y1 is in n. So because n is an R module, b times a1 y1 is also in n. So this is in the kernel of nu intersect n. So we have seen that everything in n can be written as something in R a1 y1 plus something in n intersect the kernel of nu. And to see that this is not just a sum of two submodules, but a direct sum, the argument is a special case of what we saw in part A, that you just say, well, there's no intersection between these two. What would it mean for something in R a1 y1 to be in n intersect the kernel of nu? Well, what happens when you apply nu to little r times a1 y1? You get R a1 nu of y1, which is R a1 equals 0, and it's the same argument as before. So now we have proven that you can write m and n as these direct sums involving these special elements y1 and a1 y1 and this special R module homomorphism nu. So I'm going to pause and erase, and I'll show you how to complete the proof by induction on the rank of each of these R modules. let's prove the first part of Theorem 4. The big idea is induction on the rank m of n. If m is 0, then what does that mean? There's no set of one element of n that is linearly independent. So that means that every element of n is torsion, that there's some r in the ring so that r times x equals 0. But this is a submodule of a free R module, and a free R module is torsion free. So the only submodule of a free R module that is torsion is the 0 submodule. So n equals 0 and there's nothing to prove. So this is true. So we're going to assume m is greater than 0, and we're going to argue by induction, meaning we're going to suppose that statement 1 is true for all integers m minus 1 or less. So if you have a submodule of a free module of rank m, then it is free, of rank m minus 1 or less, it is free of rank m minus 1 or less. And now we're going to apply this decomposition that we get from statement B that we proved before, that n is a direct sum of R A1 Y1 and n intersect the kernel of nu. So n has rank m. What about the ranks of these modules? Well, exercise, you can work this out directly, but exercise 3 of section 12.1 states this very nicely, which is, suppose you have an integral domain and let A and B be R modules of ranks m and n respectively. You can prove that the rank of the direct sum, A plus B, is the sum of the ranks of A and B, which is what you would expect. So you should do this exercise. I encourage you to think about it. But using that, we can see that n intersect the kernel of nu has rank m minus 1, because R A1 Y1 has rank 1. So these two numbers have to add up to m. So now we apply the induction hypothesis to n intersect the kernel of nu. So this is this submodule of n of rank 1 less. So this is free. And because of this direct sum, if you take a basis for n intersect the kernel of nu that has m minus 1 elements in it, and you add A1 Y1, which is clearly a basis for R A1 Y1, then what you get is a basis of n of size m. So n is a free R module of rank m. Okay. So what happened here is when the rank of n was 0, there was nothing to prove. We argue by induction, and this is induction on the rank of the submodule of our free R module m that we're looking at. And n intersect kernel of B is a submodule of m that has rank 1 lower than m. So we apply the induction hypothesis to this submodule and use it to say something about the submodule n that has rank m. Okay, so this is also like sort of a clever idea, because you need to find inside your submodule m that you care about, you need to find a good choice of a submodule of n that has lower rank. All right, so I'm going to pause and erase, and we'll see how to use the things that we have proven so far to prove part 2 about the existence of these good bases, y1 up through yn of m, and a1 y1 up to am ym of n. Let's do the proof of the second part of Theorem 4. And here, the big idea is induction on the rank n of m. So when n equals 0, there's nothing to prove at all. So we'll suppose that n is bigger than 0, and we'll suppose that the theorem is true for any free R module of rank n minus 1 or less, so that there exists a good basis So if you have a free R module of rank n-1 or less, along with a submodule, there's a good choice of basis for your free R module of rank n-1 so that you have a corresponding good choice of basis for this submodule that is given in terms of these ring elements that satisfy the appropriate divisibility conditions. All right, so that's the idea of the induction. Where do we find a free R module of rank n-1 or less? Well, the kernel of nu is a submodule of M, and we're going to apply the first part of theorem 4 to the kernel of nu. So this is a submodule of this free R module of rank n, and that means that it's free. That's part of what the first part of this theorem says. It says it's free of rank at most n. But what is the rank? Well, we know more. We know that M is a direct sum of Ry1 plus the kernel of nu. And Ry1, this is free of rank 1. So because this is a direct sum, we can see that the kernel of nu has to have rank n-1. And now we're in business because we can apply the induction hypothesis to the kernel of nu. So what do I mean apply it? This is playing the role of M in the statement of the second part of theorem 4. So what do we get? We get a good basis for kernel of nu. We'll call that basis y2 up through yn, which is very suggestive of how the end of this argument is going to go. We've already used y1 in this decomposition of M involving kernel of nu. So there is a basis, y2 up through yn of kernel of nu, so that a2y2 up through am is a basis of this submodule of kernel of nu and intersect kernel of nu. So this and intersect the kernel of nu is playing the role of n in this statement of theorem 4 now. We have this free R module kernel of nu that is like playing the role of M, and then we have a submodule of it that's playing the role of n. So what is true about these A2 up through AM is that these are some ring elements A2 up through AM of R with A2 divides A3, A3 divides A4, up through AM-1 divides AM. And now, by the directness of this sum, you just take a basis for kernel of nu, and y1 is a basis for ry1. And if you adjoin y1 to this basis that you have here, you get a basis for M. And it has one more element than this basis of kernel of nu did. So same idea for n. You have this basis of n intersect the kernel of nu, and then you have r(a1y1) direct sum n intersect kernel of nu is equal to n. So you add a1y1 to this basis, and you get a basis for n. So what do we need to prove? The last part of the statement number 2 from theorem 4 is we need these divisibility conditions. A2 divides A3 up through AM-1 divides AM. These are all true, but we also need to know that A1 divides A2. So that's the final thing that we need to do in order to complete the induction here. So I'll pause and erase and show you why A1 divides A2. The very last piece of the proof of theorem 4 is to show that A1 divides A2. And we're going to do this by coming up with a clever homomorphism from M to R that is specified by where you send these basis elements, y1 up through yn of M, that we now know we have. So we're going to find this homomorphism by saying that it sends y1 and y2 to 1 and sends each other yi to 0. So A1 is now equal to phi of A1y1. And A1y1 we know is in n. So A1 is in phi of n, the image of this homomorphism applied to n. Why would we bring that up? Why would we use this? Well, where did A1 come from? The ideal generated by A1 is this maximal element that we have in the set of all the principal ideals that arise from taking an R module homomorphism and applying it to n. So this element A1 is in this image. The whole ideal generated by A1 is in this image. But we know that the ideal generated by A1 is maximal in this sigma. So that means that this image must be equal to the ideal generated by A1 because it cannot properly contain it by the maximality of this ideal. All right, so now let's look at what happens with A2. A2 is equal to phi of A2 Y2 because of the way that we defined phi. And this is in phi of n because A2 Y2 is in n. But that is the ideal generated by A1. So A2 is in the ideal generated by A1. So A1 divides A2. So that completes the proof of this theorem 4. Finally. So this, I think, was by far the most complicated argument in the entire 206 sequence so far. So I'm going to pause and erase and just say a little bit about the leftover things about classification of modules over a PID that we have not proven yet. I do want to emphasize that now that we've proven theorem 4, we have also given a full, complete proof of the existence for classification of modules over a PID in invariant factor form. We've now given a complete proof of the fundamental theorem existence part in invariant factor form. And the very last thing I want to talk about is how to go from invariant factors to elementary divisors. So in this decomposition, in the invariant factor form, we have direct sums of a bunch of R modules that look like R mod the ideal generated by some A. R is a PID, so it's also a UFD. So we can factor this element A. We can write it as some unit U times P1 to the alpha 1 times P2 to the alpha 2 times PS to the alpha S, where, okay, U is a unit. Each one of these alpha i's is positive, and these PI's are distinct primes in R. This factorization is unique up to associates. So this, if you write down all the different factorizations you can, you won't always see the same prime P1, but because you could multiply this prime by a unit, but the ideals generated by each of these prime powers are uniquely determined. So you take a ring element A and you get a bunch of ideals generated by prime powers, P1 to the alpha 1, P2 to the alpha 2, and so on. All right, so what's true about these ideals? They're co-maximal if you take different pairs. So Pi to the alpha I plus Pj to the alpha j is R when I is not equal to j. The intersection of all these ideals is the ideal generated by A. Why? Because A is the least common multiple of all of these prime powers. Why bring these things up? Because the idea is to apply the Chinese remainder theorem. So by the Chinese remainder theorem, we get an isomorphism of rings, but you can see that it's also an isomorphism of R modules, that the isomorphism that you get satisfies the things that it needs to be an isomorphism of R modules. So we see that R mod the ideal generated by A is isomorphic to the direct sum of these R mod the ideal generated by P1 to the alpha 1, direct sum R mod the ideal generated by P2 to the alpha 2, plus R mod the ideal generated by PS to the alpha S. And this gives the fundamental theorem existence in elementary divisor form. So the big thing was having one of these existence results. To go from invariant factors to elementary divisors, the main thing is you take each of your elementary divisors, each of these ideals that occurs in this decomposition, and you factor the corresponding ring elements into products of primes. Okay, so what's left? What have we not yet done about modules over a PID? We stated the primary decomposition theorem. And in the case that your R module M is finitely generated, this follows directly from the elementary divisor form. You just group together all of the pieces in this decomposition that correspond to the same prime P. So in these different invariant factors, you might see the same prime appearing like once for the factor A1, once for the factor A2. So you just group all of those together and take the direct sum, and that'll give you the PI primary components. But the way we stated the primary decomposition theorem, it said something interesting in the case where M was not finitely generated also, not necessarily finitely generated. So I'll let you think about that. So I will sort of leave that as a direction for you to read about. And then there's the uniqueness in these decompositions. And this is a significant thing to prove. It's not so easy, but it's been a very long quarter. So I will leave that to you to think about. And good luck on the exam next week.